In this video, we'll get some more practice with p-series and the integral test. Throughout the course, you'll see multiple different tests for convergence or divergence of series, and you're not always told which test to use. That's going to come with practice. But for now, we're going to focus on p-series and integral test. Up first, notice that this example has a single term in the denominator involving n. That's a good indication that we may potentially be able to rewrite this as a p-series. So let's try that. Let's write this as the sum from n equals 1 to infinity of, let's split this fraction into two separate fractions. We have the square root of n divided by n squared plus 4 divided by n squared. And now that we have two separate fractions, we can break apart these two into two different sums. Sum from n equals 1 to infinity of, let's go ahead and simplify this square root of n divided by n squared. We can think of that as 1 divided by n to the 3 halves. And then the second sum, n equals 1 to infinity. And that fraction is already good to go. That's just 4 divided by n squared. Hopefully now we can see that these two are p-series. This one has a p-value of 3 halves, which is bigger than 1. And when our p-value is bigger than 1, that tells us that that series converges. This series is also a p-series. This time p is equal to 2, which is also bigger than 1. And when p is bigger than 1, we know that the p-series converges. So if we have the sum of two convergent series, we know that the overall series, sum n equals 1 to infinity of the square root of n plus 4 divided by n squared, must also be convergent. Up next, we are again testing for convergence or divergence. This time we're not given the summation notation, so we'll have to look at what we have and see if we can create that sum notation. It looks like we have some indication. We have 2, 3, 4, 5. We can think of this as being 1 divided by 1 square root of 1. So it looks like those are the n values. Notice the top, the numerator is just 1. And in the denominator, it looks like we have n square root of n. And our n values are going from 1 to infinity. We can then rewrite that as the sum from n equals 1 to infinity of 1 divided by n to the 3 halves. And notice we again have a p-series. P, in this case, is 3 halves. And that is bigger than 1. When your p-value is bigger than 1, we know that the series converges. In this example, notice that the denominator has more than one term in it, so we're not going to be able to split up the sum into two different sums like we did in the first example. So we're probably not going to be able to rewrite this as a p-series. So our next test for now is the integral test. Let's think of the sequence as a function. So we'll take that sequence and rewrite it as a function of x. From here, we need three things. We need continuous, positive, and decreasing. And it looks like this is continuous. We don't have any issues with continuity. It is positive for values 1 and bigger, the function is positive. And the final thing we need to test is it decreasing? Now, intuitively, as n gets bigger, or x in this case gets bigger, the denominator is going to grow faster than the numerator. So it looks like it will intuitively be decreasing because the denominator grows faster than the numerator. But if we wanted to really prove it, we would need the first derivative. So let's try that. Let's take a look at the first derivative. We have x to the fourth plus 4 times 3x squared minus x cubed times 4x cubed, all divided by the denominator squared, just using the quotient rule. Next, we'll simplify that. That gives us 12x squared minus x to the 6 divided by x to the 4th plus 4 squared. We'll factor out an x squared in the numerator. It'll give us 12 minus x to the 4th divided by x to the 4th minus 4 quantity squared. And we want to see where this is less than 0. Because if the first derivative is negative, less than 0, that means the original function is decreasing on that interval. So if we set the numerator equal to 0, let's focus on this second factor, because the first factor will just give us 0. If we set this piece equal to 0, we get x to the 4th equals 12. Take the 4th root of both sides. And the 4th root of 12 is roughly 1.86. So it's not quite where we wanted, but so it's not quite where we wanted. We wanted it to be smaller than 1 or starting at 1 because our series is starting at 1. But we can say that it is decreasing on 2 to infinity and go from here. So from here, we will use the integral test. That is the integral from 2 to infinity. Remember, we can't start at 1 because we're not for certain decreasing on 1 according to the calculus. X cubed divided by x to the 4th plus 4 dx. We'll then use a limit as t approaches infinity of 2 to t x cubed divided by x to the 4th plus 4 dx. From here, let's do a u substitution. Let's let u be x to the 4th plus 4. du is 4x cubed dx. Then we'll divide by 4. 1/4 du is x cubed dx. Now rewriting that limit, we have the limit as t approaches infinity. Integral 2 to t. We have, again, rewriting this in terms of u, we now have 1/4 times 1 over u du. Continuing with this, we have limit as t approaches infinity. Let's now evaluate that integral. We'll have the constant 1/4 out front. Integral of 1 over u is the natural log. So we have the ln of u, but I'm going to go ahead and replace u with the value we have for u. x to the fourth plus 4. And we want to evaluate this from 2 to t. So we now have limit as t approaches infinity of 1/4 ln of t to the fourth plus 4 minus 1/4 ln of, let's see, if we plug 2 in, we'll get 2 to the fourth, that's 16, plus 4 is 20. And now looking at as t goes to infinity. Inside this natural log argument, we have infinity raised to the fourth. That's a really big number. We're taking the natural log of a really big number, which means that this is going to infinity. It is diverging. So if the integral diverges, we can say that the original sum also diverges. And now we can go back to n equaling 1. Again, this was testing for 2 to infinity, but if 2 to an infinity diverges, then 1 to infinity definitely also diverges. So continuing to just rewrite the original, n to the fourth plus 4, we know that this diverges due to the integral test. In this example, we again want to determine whether or not the series converges or diverges. It looks like it's not going to be a p-series, so we'll use the integral test. We'll let f be x e to the negative x squared. Don't let those k's throw you. We're just using k's instead of n's this time. And this may be a little easier to see if we write it as x divided by e to the positive x squared. We again want to determine if this is continuous, positive, and decreasing. We know it's continuous. We can see that it's going to be positive. And for decreasing, let's again take the first derivative. So f prime, we have e to the x squared times 1 minus x e to the x squared times 2x. All of that is divided by e to the x squared quantity squared. It looks like we have e to the x squared in the top and bottom. We can reduce that to get 1 minus 2x squared divided by e to the x squared. And again, if our first derivative is negative, then we can say that the original f is decreasing. So let's figure out where it is negative. Let's set the numerator equal to 0 and figure out where that's happening. Let's see, we get 2x squared equals 1. X is equal to the square root of a half, which is roughly, that's 0.7. So we can say that it is decreasing on 1 to infinity. Since we're starting at 0.7 decreasing, then it's definitely decreasing from 1 to infinity. Next, we'll use the integral test. We have the integral from 1 to infinity of x e to the negative x squared dx. We take the limit as t goes to infinity, 1 to t of x e to the negative x squared dx. It looks like a u sub is again going to help us, so we'll let u be negative x squared. Du is in negative 2x dx, dividing by negative 2, we get negative 1/2 du equals x dx. Now we can rewrite this as the limit as t approaches infinity, integral from 1 to t. We're now using our u values, so we have negative 1/2 e to the u du. This will be a little bit easier to integrate now. We have limit t approaches infinity of negative 1/2 e to the u. But let's replace u with our u value, negative x squared. And we want to evaluate that from 1 to t. We now have the limit as t approaches infinity of, plugging in those limits of integration, we have negative 1/2 e to the negative t squared minus negative, we'll make that a plus, 1/2 e to the negative 1 squared. And now, evaluating the limit, t is getting really big. Squared, that means this piece is going to 0. And over here we just have a constant that is 1 divided by 2e. So our integral converges. And if the integral converges, that tells us that the original series k equals 1 to infinity of k e to the negative k squared also converges due to the integral test.